Hi, this is Dr. S and welcome to video 10 of my series on aromatic chemistry for OCR A-Level. In this video it's going to be your chance to try and apply the knowledge that you've developed about the mechanisms of electrophilic substitution of benzenes to unfamiliar situations. Now this is where the exam goes into an application type mode, so this is a more difficult skill and it's something that the top grade students would need to master. So I'm going to give you some unfamiliar mechanisms. So they might be related to the mechanisms you've done, but there'll be something different. So you've got to try and then apply your knowledge of what you've learnt to try and do them. So I'm putting these three mechanisms on the board, if you could just see them. And what I'd like you to do is, when you're ready, pause the video and try and complete the mechanisms for each of those three reactions. Have a go at it, pause the video and come back when you're ready. Okay, I'll go through each of the three reactions in turn. So the first one is the bromination one at the top. So this is the mechanism that we should be expecting. Generation of the reactive electrophile Br+ using a halogen carrier. Movement of a pair of electrons from the pi system to the Br+ to create the intermediate. Remembering that the horseshoe in the intermediate opens up towards where the substitution is, so it's on the 2 position. Then movement of the pair of electrons back from the C to H bond into the ring to produce the product. And an H+, which then reacts with the FeBr4- ion to regenerate the halogen carrier and the HBr. Okay, the second example was a nitration. Again, generation of the electrophile is the first step. So the reaction of concentrated nitric acid and concentrated sulfuric acid to produce the nitronium ion. The nitronium ion can then have a movement of a pair of electrons from the ring towards that to create the intermediate. Here the horseshoe shape opens up towards the bottom. Movement of the pair of electrons from the C to H bond back into the ring to produce the product and the H+. And then the H+ can react with the HSO4- to regenerate the sulfuric acid. It's worth noting on this one that here the nitro group looks different. That's because it's backwards, if you like. NO2, O2N. That's to show that it's the nitrogen that's actually bonded to the carbon. So if you're on the left-hand side of a benzene ring, you often see groups looking slightly different. That's something you'll get used to. Okay, and the third one was really unfamiliar. The third one was a reaction of sulfur trioxide with benzene. Now this is really difficult because here there's no idea that there's a generation of a different electrophile. You don't know what's going to be produced. Now actually that's a kind of hint. The oxygens are all very delta negative, which makes the sulfur quite delta positive. Actually it's a strong enough electrophile to react with the benzene on its own. So thinking about where the electrons will be attracted to, the electrons in the pi system are going to be attracted to the delta positive sulfur. Now that causes a slight problem because that's a bond from the benzene to the sulfur. The sulfur's already got 6 bonds. So one of the other bonds on the sulfur has to break, but the hint is that in the product there is an O-, which suggests that there's a movement of electrons towards that oxygen at some point. So that would be here. As the movement of electrons comes towards the sulfur, one of the double bonds will break and move the pair of electrons onto an oxygen, creating an O-, which you can see in the intermediate here. The rest of it's the same. The horseshoe shape opens up towards the substitution position, movement of a pair of electrons down from the C to H bond to produce my final product. Now what's worth noting here is the picture I drew on the first page actually had this group in a different position. It looked like this. And that can confuse some people. But I just rotated the benzene ring 60 degrees anti-clockwise to produce that. It's exactly the same thing, it's just rotated. Okay, then we produce the H+. Now actually, in reality, what would then happen is there's a lone pair of electrons on that oxygen, and that would transfer to that hydrogen to actually put an H onto here. So actually what you would get as the final product is this. However, that's not what the question asked. The question asked for the ion. So that was enough. That one has actually been asked by OCR in the past. Okay, so I hope you did well on those three. I hope you feel confident on your mechanisms. I hope you'll see the value of taking the time to get the mechanisms spot on so that then you can apply your knowledge. My next installment of this mini-series is going to be about phenol. So next week, we'll be looking at phenol. Phenol looks like this. It's a benzene ring with an OH group directly attached. So if you'd like to do some pre-reading, look up phenol. And my next set of videos will be about phenol and its reactions. Okay, I'll see you then.